I hope you can see the screen. So I will take you through the slide pack, and we'll discuss. I mean, you will see some of the things we have already discussed, and then we will cover up the rest about paleomagnetism. So at the times in the Earth's history, the magnetic poles have been interchanged, and this is what we call as polarity reversals. We talked about it before. Occurs at regular intervals in million years of time scale. Times of reversals can take place also, in the, I mean, kilo year to million year. We talked about it before. It can be geologically short, rare to find rocks from the transitions. Okay, when essentially such transition happens or the flip happens, whether you can find rocks carrying such signatures, such rocks are rare. Current state of field is normal. Reversed state is termed as reverse polarity or R polarity, and normal polarity is termed as N polarity. Excursions of the magnetic poles also occurs. We'll explain that later on. This is essentially the change in the angle that we talked about. The rocks retain magnetism acquired long ago, often when they were formed, and this is what we call as paleomagnetism. Yeah. Consider a pile of tertiary lava. So we are trying to give you an example. Each eruption cools in few years. Okay, so the lava that comes out, and then in few years it actually cools down and forms the volcanic rock. Records instantaneous field direction, and this is what we have called as remanent magnetization, right? So when the rock essentially forms, we are giving an example of an igneous rock, and it comes out to the surface. It chills down, and while chilling down, it is actually taking up the direction of the then magnetic field of the Earth. So deposited over thousands of years, the lava pile will average out secular variation. Okay, so we talked about that. You remember when we essentially drew that stereo net, we said from each of these cores, I will find number of points. Yeah, if secular variation would have not been there, they would have all lied on the same point. But because we get the scattered, we simply get because of the secular variation. And we discussed what secular variation is. So samples of rocks are required. To carry out the analysis, we talked about it before. So the samples have to be oriented, that is must. So generally a short core is drilled out. We talked about it. Okay, penetrates through weathering. I mean, you generally need fresh rocks to carry out such analysis, not weathered rocks. Very important to have three-dimensional orientation on the sample. So the samples must be oriented, right? Usually 6 to 8 samples separated by few meters. That is what you collect from the field from each rock unit. Okay, like we have given you the example of A, B, C, D, E, F. In each of them, at least 6 to 8 samples, which are separated by a few meters, are collected so that you get a good statistical average. So in the laboratory, short cylindrical cores are drilled out. Okay, and then of course you measure its total magnetism, and then you take so the cylinder is spun, causing its magnetism to produce current in a nearby coil, which can be used to measure the magnetic field. This is repeated for other two orthogonal directions. Convert the data into declination and inclination using sample orientation. Okay, don't worry about this part. You finally calculate declination and inclination from a sample. Okay, and then perform for several cylinders from each core, plotted on a stereo net. Give a stereo plot of the directions: positive inclination downward, is plotted with open circles, as we have discussed in the last class. If the samples clustered, we can assume that the magnetization has not changed over time. Okay, and the clustering essentially happens because of the secular variation. And you know about how declination and inclination is plotted on a stereo net. Okay. So magnetization is usually reported as mean direction with an error. We talked about it in the last class. We assume that the samples are scattered randomly. Statistics of small numbers of the samples is dicey. So more samples is always better. Error is represented with alpha 95. That means 2 sigma standard deviation. A cone with the half angle has 95% probability of containing the true direction. So we talked about this before. Okay. So these are all the so after the demagnetization, these are all the, after demagnetization, you measure the inclination and declination of each core, and then you plot them in the stereo net, and you do your statistical analysis to find the mean. So that will provide you the mean D and I for each rock unit. So rocks magnetized at the same time but at different latitudes have different magnetic directions, which is inclination, make it difficult to recognize if these rocks or the continents are riding on or have moved apart. We will discuss this point later on. We calculate the position of the magnetic north pole at the time of magnetization. Actually, when the poles was, where the pole was relative to the rock sample, this is what we call as apparent pole. So, for example, I'll give you. So here I need to explain this part. Okay. Okay, let me go with the slide and then I'll explain. So what it means that we explained up to calculating paleolatitude. Okay, so from paleolatitude you need to calculate something called apparent pole or VGP or virtual geomagnetic pole. So the virtual geomagnetic pole is the relative position of the pole, the relative position of the magnetic pole with respect to the continent. Relative position of the magnetic pole with respect to the continent, and I'll give you an example how to do it properly. Okay. For example, a rock was formed at the equator. That means there the I will be is equals to 0. Later it moved to the south pole. So I is equals to 0 inferred it was magnetized at the equator. Okay. So so first you take the sample out, okay, and we talked about this tan I is equals to 2 tan lambda. So you find your inclination, whatever it is, and from there you calculate your uh, magnetic latitude. Okay. And from magnetic latitude, you have to now calculate your uh, virtual geomagnetic pole. Just tell me one thing, up to calculating paleolatitude, is that clear for everyone? Have you all understood how the paleolatitude is calculated? Up to tan I is equals to 2 tan lambda. Have you all understood? Okay, excellent. So now let us try to calculate. Now let us try to calculate the virtual geomagnetic pole from that data. Okay, so we will work with a real example that is given in the presentation. So the data, so I'll just explain to you once more. So this is a rock unit which is currently is of your interest. Okay, and then you have taken out 6 to 8 samples out of it. All of them are oriented, right? And then from each sample, from each of these samples, okay, you have drilled out cores. Okay, another 5 to 6 cores out of each sample. Cylinders, small cylinders. And then the next step is you demagnetize each of these cores. And then when you find the, you know, remanent magnetization, yeah, MR, that is the stable magnetization after demagnetization. So of that MR, you actually calculate your, so this is east, north, Z, and here is your MR. And then this is the horizontal projection. So this is my I have found out, and this angle is my declination. Okay, so I have got my inclination, declination, which I have got by, plotting them in a stereo net. And the value that I have got is the inclination is uh, the inclination is 49 let me see. Yeah, the inclination is 49 degrees. So, and the declination is 20 east of north. Okay. So I have got inclination is 49 degree, means positive, right? So that is, it is pointing downward, it is in the North Pole. And then, I have got my declination to be, how much did I say? Was 20 degree east of north. 20 degree east of north. Okay, these two I have got. So so that means 49 degrees declination, 20 degrees. So, it will be somewhere here and 49 degrees. So here will be my inclination and declination plotted, and which is nothing but, the inclination and declination plotted from each of these cores, right? It's the mean direction. So that is what is this value representing. Okay. Now, first thing I will calculate my paleolatitude. Okay. Paleolatitude is how tan I is equals to 2 tan lambda. And to make my job easier, I can actually already create a chart, not to do the calculation. So that means 49 degree of inclination around 50 degree, that will mean of a paleolatitude of around 30 degrees. Okay. So if you do it here, if you replace it in the formula, it will give you the same result. So lambda, which is my magnetic latitude, is how much we calculated? We saw it to be 30 degree. Okay. 30 degree. 30 degree in the northern hemisphere. Okay. Now you see the current location of this rock. The current location of this rock is north 10 degree latitude. So the current location is north 10 degree latitude. The rock is currently sitting at north 10 degree. So that means it has moved. It was formed at 30 degree and it has now moved to 10 degree. If you do that little bit of an adjustment of magnetic latitude to real latitude, maybe 1 or 2 degrees it will differ. Okay. Or 5 degrees, 10 degrees, who knows, whatever. So you do that calculation, but then let us for the time being, let us say, just for the sake of argument, we say lambda true latitude actually is, it's also 30 degree, just for the sake of argument, okay, sake of understanding. Let us say this is 30 degree as well. So that means the right now it is at not 10 degree latitude, but while the formation of the rock, it was at 30 degree latitude. The next thing we have to calculate is the virtual geomagnetic pole, VGP, and VGP refers to the position of the pole, the relative position of the pole, relative position of the magnetic pole, position of the magnetic pole with respect to the continent, the continent at which this particular rock is sitting now, okay, with respect to the continent, relative position of the magnetic pole with respect to the continent on which the rock is sitting, right? I'm not writing that. Now, the first thing you have to do is to calculate the latitude of the VGP. So, latitude of the VGP will be equals to 90 degree minus lambda. Okay. So, that means it will be 60 degrees in this particular example. Okay. So, the latitude of the VGP is 90 degree minus lambda, which is 60 degree for this particular example. Now, what you need to do, you can actually calculate the longitude of the VGP as well. So, what does that mean? That see, this is my Earth. This is the equator. Okay. Now, suppose this is the position of the continent now. Okay, this is the present position. So P is the present position. Okay. So now what I will do, I will draw the longitude as well, pole to pole. Now I said that the for VGP, the paleolatitude is 60 degree. Okay. For the VGP, latitude is 60 degree. Okay. So this is, this is essentially 10 degree north, right? This is the current position of the continent. So 60 degree north will be somewhere here, right? If along the same longitude, 60 degree north will be somewhere here. And now this is 60 degree north. Now we need to use the declination value. What is the declination value that we have got? We have got the declination value being 20 degree east of north. Okay. So what I will do, so now I have these longitudes, So what I will do, I will go 20 degree east of north. So declination value was 20 degree east of north. So I will go 20 degree. So maybe these are my 10 degrees interval, 10 degrees, 20 degrees. So I'll go towards east. Okay. I'll go towards east, and then I will plot my 1, 2. I'll plot my point here. So this angle is 20 degrees. So if it would have been 20 degree west of north, then I would have gone on the other direction. Okay? So this point will be my VGP. So this is my virtual geomagnetic pole with respect to the continent during the formation of the. So this is the VGP. The VGP, the relative position of the pole, magnetic pole, magnetic pole during the formation of the rock. Okay, so if I recap from the declination and the inclination value, the first thing that you calculate is the paleolatitude, which is very simple. You take your inclination value and you do tan I is equals to 2tan lambda, and then you plot your, then that is your paleolatitude. You are not able to actually find out the longitude of the uh, continent. That's not possible in this work. But then you can actually calculate the uh, virtual geomagnetic pole. How the virtual geomagnetic pole is calculated? So 90 degree minus uh, paleomagnetic latitude is equals to your latitude of the VGP, and longitude of the VGP is calculated by using the declination value. Okay, is that clear, everyone? Just tell me. Needs to be clear.
Yes, sir.
Yeah, Adil.
Sir, can you explain how did we, after calculating the latitude of the VGP,
Yeah,
okay, after calculating paleo latitude,
yeah.
we calculated VGP.
Yeah, we calculated VGP. So VGP, the pole, the virtual geomagnetic pole, have two things. One is latitude, one is longitude, right? So the
Yes.
latitude is 90 degree minus your paleo latitude. Okay. So if you have got with your tan I is equals to 2 tan lambda, if you have got 30 degree, then means the latitude of the VGP is 60 degree.
Uh,
Okay.
o- okay, does that mean that the pole was 60 degrees north?
No, this means it is the relative position of the pole with respect to the continent.
Okay, and acha, okay,
Yeah.
and after that, how did we plot it?
Sorry?
After getting this value of 60 degree, how did
Yeah.
we plot it? Can you explain that part?
No, that's what I did now. So 60 degree. So that means suppose this is my current position of the uh, uh, of the continent. Okay. So this is 10 degree, right? So along the same longitude, I go 60 degree. Okay. So that is my
Okay.
latitude, but that is not my position. I have to now go. I have to now calculate the longitude as well. Then I use my declination value. Okay. So from the same point, I move 20 degrees towards the east. So this is, so suppose, say for example, this is 0 degree. Okay. So I move 10 degree, I move 20 degree on the small circle. Okay. I move on the small circle 10 degree, 20 degree. And that will give me, from this point, that will give me my virtual geomagnetic.
Okay, sir.
Is it
So
clear?
calculate VGP with respect to the current position of the rock, right?
No, it's VGP is essentially calculated. So your 30 degree north, your paleo latitude will be somewhere here, na? 30 degree, 10, 20, 30. This is where your paleo latitude is.
Yes, sir.
This is 60 degree. No, VGP is with respect to the ancient position. I mean, when the rock was formed.
Okay.
So that
Okay,
means
sir.
I don't exactly know where this rock was, right? Because I don't know about the longitude. That's right. You
Yes.
understand my point. I
Yes, sir.
don't know where this rock was, whether the rock was here, whether the rock was here, whether the rock was here, whether the rock was here. I don't know, right? But if the rock would have been here, then the position of the pole would have been here. That's all I'm saying.
Okay, sir.
Understand my point?
Yes.
Let me explain once more for everyone's sake. This is my Earth. This is the equator. Okay, and these are my latitude lines. The latitude lines are, as you know, are the small circles, right? This is how they look like, right? And then I will to draw longitudes. They are my great circles. So for the sake of argument, we said, so this is north, this is south, okay? This is east, this is west. Remember these, the thing that I am drawing right now is magnitude, latitude, magnitude, magnetic latitude and magnetic longitude, okay? You have to give a little bit of shift to calculate the true latitude. I'm just drawing the magnetic latitude and magnetic longitude. So suppose this is my position of present day continent, okay? So what does that mean? It has a latitude of you know 10 degrees and longitude of whatever it is, say 180. Or let me give a more generalized, because this is a bit too, what is that called? Suppose this is here, okay? This is my the current position of the rock, okay? And in that I have found a rock unit, okay? After doing all that thing, I have found out my inclination being, as I said, 49 degrees, and declination being, I'll use, you know, uh, 20 degrees west of north. Okay? So from here, inclination value, I calculated my paleo latitude. That will be 30 degrees. Okay. So this is 10, 20. Suppose I need to increase the intervals, of course, here. Suppose this is 30 degree. So this is my paleo latitude. Now we cannot calculate the longitude position. Okay, the continent could be here, could be here, could be anywhere. I don't exactly know, because I'm not able to calculate the longitude from paleomagnetic data. It could be anywhere. But if the rock would have been here, okay, then where would have been the VGP? Where would have been the virtual geomagnetic pole? Okay, where would have been the pole? That is what we are trying to do. So I have got, if the paleo latitude is 30 degree, that means, so this is 30 degree, okay? This is 10 degree. If it is 30 degree, then my uh, paleo lat for VGP will be 90 minus 30. That means 60. So I'll go here, where here, 60. And then I will use my declination value, 20 degree west of north, then 20. So that will bring it to me here. So along the small circle, I am moving 20 degree towards west in this example from the current position, and that will provide me another point. So what does this mean? That if my continent would have been here, then with respect to the continent, the pole would have been here. So this is the with respect to the possible location of the continent. Is it clear now, everyone? I'm glad it is clear because it's a little bit of a tricky concept to understand, but I hope it is
Uh,
clear. If the continent would have been there, then the pole would have been there. Yeah, Srivats.
Sir, I have a doubt. While calculating VGP latitude,
Yeah,
isn't it supposed to be 90 minus actual latitude?
I'm doing everything on magnetic latitude right now. So after you calculate your VGP, both latitude and longitude, you can do the whole calculation on magnetic latitude and magnetic longitude, and then do that transformation. That is
Okay,
also
okay,
fine.
got
Yeah. Or
okay.
start with the you can do the your I mean, it's all about putting things in relative positions, right? So what you can do, you can actually think what is the tell you what is the magnetic latitude of today of that particular place, and you can start it from there as well. It will still give you the same result.
Okay, sir.
Yeah.
Okay, thank you.
Anything else? Okay, so let's continue. I hope it was clear for you how the apparent pole is created. Okay, so if the apparent paleo pole is not the present magnetic pole, then the rock must have moved. So the declination is not due north, then the rock must have rotated. Okay, you understand this by now. The inclination does not correspond to the current latitude. The rock must have moved north or south or got tilted. Tilting can only be recognized and corrected. Forget about. Okay, so you have to remember another thing. I think it was I forgot to mention. So suppose I have got a rock sample whose plane. So this is a horizontal plane. The rock sample, the top plane is horizontal. Okay. Now, when you will calculate the, remanent magnetization vector, okay, this will be the true remanent magnetization vector, right? But if this rock itself is tilted, you know, if the rock itself is tilted and the tilting has happened after the formation of the rock, of course, after the formation of the rock, the tilting has happened. After the RM was acquired, you know, what would happen to this vector? So this vector will be further rotated, right? This vector will be further rotated, okay, to accommodate the tilting. So what I need to do, I need to do a tilt correction. So tilt correction means I have to essentially rotate my RM vector in a way that it gives me the orientation of the vector, uh, assuming that the rock is horizontal. Okay, so I have to remove the physical tilt of the rock from RM if I am collecting the sample which is already tilted, which has a dip. Understand my point? Because as if it was uh, you know, let's try to see that example. For example, the rock was formed in the equator. Okay, so that means that will have no inclination. Right? This is how my RM would look like. But then, if this rock is then deformed and then the rock is tilted, what would happen? This vector would look like this, right? Because you are physically rotating the rock, and so would your RM would do. Okay, but that is not the true RM because the rock was formed in the equator. The inclination must be zero. So I need to essentially rotate this RM back to the original position to correct for the tilt, the physical tilt of the rock. Okay, and this is what we call as tilt correction. Now, for example, the there is another important thing that we are going to talk about now in the same context. That is what we call is APWP, or apparent polar wander path. Apparent polar wander path. Okay, and let us look at the same example. Okay, so you have a pile of rock A, B, C, D, E. Okay, and then what I am drawing? I am drawing so this is my equator. I'm drawing the VGPs. Okay, I'm drawing the VGPs. So VGP A, VGP B, VGP C, VGP D, and so on and so forth. So, and then I can join them through a path, and this path is called APWP, apparent polar wander path. This apparent polar wander path can actually help you to calculate the plate velocity. Yeah, this apparent polar wander path can help you to calculate the continental velocity, okay, the drift velocity, because we know the ages of these A, B, C, D, E, F, E. Okay, so say for example, I know you know A actually formed in 20 million years. In 20 million years, 20 million years ago. B happened before 10 million years ago. So the VGP actually moved by then this distance. So I can essentially calculate. So within that 10 million years, perhaps it moved for, I don't know, 1,000 kilometers. Okay. So 1,000 kilometers by 10 million years would give me the velocity of that continent that we are studying. Okay. Now, if we another interesting thing that you can do with apparent polar wander path is, suppose I am analyzing two rock sections. Yeah. Suppose this one is in India and this one is in Africa, or Africa and let's for the timing, yeah, India or Africa, any two continents. Okay, and I happen to observe that their apparent polar wander paths are kind of matching till a certain time. So this is, suppose this is suppose these are for Africa and these are for India. They are matching. two different rock units sitting in two different continents, okay? But their apparent polar wonder paths are matching. Okay? And then after certain time, say this is 50 million years ago. I'm just giving example, huh? 40 million years ago, this 20 million years ago. And then after 20 million years, India's BGP goes this way, and Africa's BGP goes this way. What does that mean? That means that India and Africa till 20 million years were together, part of the same supercontinent, and then maybe after 20 million years, they got separated. Okay, they got drifted apart. Okay, and hence they had different virtual geomagnetic pole. Now, if we look at it in a different way, suppose we see that for two continents, okay, I see this is to 100 million year ago, this is 80 million year ago, this is 60 million year ago, this is 50 million year ago, 40 million year ago, 20 million year ago. What does that mean? That up to 60 million years, they were separated. And after, from 50 million years ago, these two continents actually got back together. They got collided. They got back together and formed a single continent. And their virtual geomagnetic poles right now are matching. Okay, so these apparent polar wonder paths essentially can help you to establish the story of continental drift, as well as which continents were together, which continents got apart from each other. Okay, so if you look at any beautiful videos that you find in YouTube, which shows plate tectonics and how the plates essentially evolved from since the beginning of the Earth, since the formation of the protocontinents, and then how they came close to each other, they got apart from each other, and all such stories are built up by calculating apparent polar wonder paths from their rock records. Okay, that is the only thing that you can use to form the pathway for continental drift. Okay, to understand how the continents essentially move. So you can see here examples. You can see here that, yeah, these two continents were together, and then essentially they moved apart. Here too, the APWPs are excellent to do such studies to understand whether the continents were together or whether they were, they moved away from each other. Okay, so that's all I wanted to say in terms of paleomagnetism. Anyone is having any question? So what you have to do, you have to go back and read Lowry's book in for good amount of time, and I hope I could make everything clear to you how these calculations are done. Okay, and when you do the assignment, for many, I mean, for a lot of you, I think I have chosen papers on paleomagnetism, and I have chosen for some the gravity and magnetic anomaly, and for some I have chosen the application of anisotropy of magnetic susceptibility. All these topics I have talked about in the class, but then, yeah, if you read the papers, it will be even more clearer to you. So the idea is when you finish your assignments, you share it with me, and also you share it with the whole class, so that everyone goes through the presentation, and you in no time you have all read 9 papers, right, on different aspects where truly these geophysical techniques have been used to practical purposes. Okay. Anything, any question that you might have?
Hello.
Yes, Adil.
Sir, let's say I have a highly viscous lava
Yeah.
and it forms in a downward slope land.
Right. So
So,
there also you have to do the tilt correction.
okay, okay. Why would I do the tilting calculation in that case?
Because there is something called gravity settling as well. So what happens? Suppose I have a particular rock, right? I have a particular mineral grain. Okay, so uh, it will acquire its magnetization because of the uh, then magnetic field, and it gets arrested. But then, because of the slope, perhaps there could be a possibility of the whole grain being rotated. Okay, so you have to make sure, you have to establish that indeed such grains have rotated. If you can establish that such ferromagnetic grains have rotated, then you have to do the tilt correction. And if you can establish that they have not rotated because of viscosity, then you don't have to.
Oh,
So
okay,
it
sir.
will depend on whether you have to physically prove whether that grain together with the magnetic moment has rotated.
So, are there any methods for that? In
Yeah, there are methods.
Okay, sir.
Yeah, you can test. It's very easy. I mean, you have to plot both of them in StereoNet, and using some geometry. If you see, they are kind of falling together. Yeah, then you know that it's correspondent to the tilt. Okay,
Okay,
and
sir.
then you have to remove that tilt. Simple. It all depends on the statistics. You have to more data. If you collect more data, of course, you will have better chances of understanding whether such corrections are required or not.
Okay, sir.
Yeah. Anything else? Okay, so next class I will start with a new chapter. But even incidentally, the new chapter time also falls on a pre-recorded lecture. So just tell me, someone, do you want me to continue the new chapter? Because I want to introduce some very new things on what is that called, on stress, strain, elastic wave propagation, and the elastic properties of the rock. Do you want it to be in a live session, or do you want it to be, you are happy with a pre-recorded lecture? Can someone just yes, and I want to hear from more people. Yeah, I also like it to be a live lecture, but you don't always you can't always control such timings. So then what I will do, I will skip from, because anyway you are doing your assignment, I will skip from having a pre-recorded lecture this weekend. But I think the next week is your mid-semester break, isn't it? Yeah. So then we will start with the new chapter after your mid-semester break. Okay. Then I think we should be fine. We are doing okay with the timings, so that is not a big deal. So the next chapter we will start with seismic. But before we get into actual seismic, we need to know few about rock rheology. I mean, how a particular rock would behave when you subject it to elastic collision. Okay, because the movement of elastic wave through the earth means you are subjecting it to elastic collision. Okay, so we will do a good amount of mechanics before we actually get into the seismic. So in this particular chapter we are going to learn about earthquakes. There are two branches of seismology. One is earthquake seismology and another is exploration seismology. In earthquake seismology, we will learn a lot about earthquakes and how do they work, what is the mechanism, and what does essentially earthquake magnitude mean, and so on and so forth. So a bit about earthquakes. And the other one is, of course, the seismic section that you prepare for oil and gas exploration. We will also learn. So you create a man-made earthquake, and see how that particular elastic wave propagates through the earth. So it's a very interesting chapter. But before that, I think we need some pre-work, some ground rules to be established, so that we can proceed with the actual chapter. Okay, so we will do it in a live session. That will be on uh, 28th of October, isn't it? The first class we are coming. Do you know when is your, the end semester examination, the final examination? Which month, which week? November. In November, which week is it? You have idea? Is it in December? Okay, so we have enough time. No problem. All right, then I will stop it here. Let me know if while you read the book, if you have further doubts. I would be happy to. Okay. No, so we have enough time. No worries. So let me know if you have any questions while reading the book. I think we will. I would be happy to answer. Thank you very much.